All right, so for 7.4, we're going to continue 7.4. Let's just refresh real quickly what we did last lesson. So similar triangles have the same shape but different size. Same shape means that all of the corresponding angles will be equal, as we established. Now we can find pieces of similar triangles by using the ratios, and we did that yesterday in class as well. We continued to explore, diagrams like this, where we have one triangle nested inside of another one, and we were able to identify side lengths and things like that. So AC, that side length, would be the sum of 5 plus 4, for example. Okay? Yeah, question?
In that triangle,
Yeah.
would it be like two different shapes though? Because the top triangle is a triangle, but then the bottom is like a trapezoid.
Yeah, so okay, so watch this. This angle C right here is part of both triangles. So it's the same in both triangles. Here's the small triangle that C is a part of. Whoa, that line didn't work so well. Here's the small triangle, right? And C is a part of that. But here's also the larger triangle that C is a part of. See, C is a part of that one too. So we know that C is the same for both. And then it's saying that there are similar triangles here. So that means that this side is parallel to this side, which means that this angle has to be equal to this angle, and so on. This angle right here, we don't know what it is, but it has to be equal to that one because they're also corresponding. So if we were to split these up, then it would look like, this small triangle right here, and then the larger triangle right here, and they would be similar. So that's C, just like that C. This is 4 and 4. This would be 9 and 9. And we found out that Y was 9. See that? So yeah, they are, even though they're nested, kind of one within the other, they can still be similar triangles that you can pull out of there. All right? And yeah, we did look at this question, number 6C, and that was a question that we had just done as well with that a similar example, right? So one triangle nested inside the other. Okay. Good. Any other questions about what we did yesterday before we finish off the lesson? Okay. All right. Well, let's take a look at example 4. Should be in your notes in front of you there. I'm going to show you two different ways to do this. And again, one might be easier than the other. So let's go with the method that we use most of the time, which is actually outlined here in the work. So it's already kind of started for you. Let's read the question. It says the length of the monument's shadow is 20.5 meters. And so that's actually indicated on the diagram right here. 20.5 is the length of the monument. So here's the monument. It's the length of its shadow. If they didn't give you the diagram, what you want to do is you want to draw a diagram. Okay? It's very, very good to have a picture of the word problem, and then to put the pieces that are in the word problem on the picture one at a time, so that you can look at the word problem and the picture, and you can see what's missing and you can see what's given. Also, it's easier from the diagram to see where the similar triangles are. It's tough to imagine the similar triangles when you just read, so you do have to draw a diagram, okay? If the diagram's already there, then great, you can work with it. But if there's no diagram, I encourage you to draw at least a rough sketch and place all of the information on the diagram so you can work with that. Okay, let's keep going. Joan's shadow, so here's Joan right here. That's Joan, this girl right here. Her shadow is 4.1 meters. So that would be the length from where Joan is to the edge here. Okay, that's in the picture, that's her shadow. So we've got two shadows, one for the monument, this big one, 20.5 meters, and this little one for Joan, 4.1. If Joan is 1.2 meters tall, so that is this length right here, 1.2 meters, calculate the height of the monument. And so what's unknown is usually represented by a variable. Okay, so an unknown piece, usually a letter, is represented by the unknown piece. So we're going to use all these numbers in a simple ratio, just like we've been doing. And the great idea is to use the corresponding parts of the similar triangles as a ratio. For example, the monument's shadow. Okay, so the monument's shadow divided by Joan's shadow would be a great place to start for setting up this proportion. or these equal ratios. So the monument shadow is 20.5. Now, we got to make sure that these are all in the same units, and if they are, you don't have to write the units in every step of your work, okay? So as long as they're in the same units, because we might have to do a little conversion first. If one was in centimeters and the others were in meters, we would have to convert everything to the same unit, right? But if they're all the same units, you don't have to put the units in the work for me, okay? So 20.5, Joan's shadow is also given, isn't it? 4.1, okay. Equals, now we've got this, so we've got this pair taken care of. Now let's take a look at this pair, which would be x, the monument's height, over Joan's height. So these are corresponding parts to the similar triangles as well. So 1.2. So we've got monument on top, awesome. We've got Joan on the bottom, awesome. Okay? And now we simply solve. So we got to get x all by itself and in the top, the numerator. Okay? We can't have x on the bottom and leave it there. We have to have x in the top. So x is already in the top. That's awesome. So in order to get rid of a divided by 1.2, I'm going to multiply by 1.2. And what I do to one side, I have to do to the other side of the equation. This is equal to the same as cross multiplying here. So 1.2 on the top and 1.2 on the bottom of a fraction like that, see? It just gives you 1 over 1. So they kind of like they go away. Over here, x is going to be equal to the product of 1.2 times 20.5 divided by 4.1. And you can do that on your calculator all at once. So on 1.2 times 20.5 divided by 4.1. All right. And that looks like it's 6. Did anyone else get that answer? 6? Awesome. Okay, question?
So when you do like the constant time on each side, will it always be the like the denominator on the right?
Well, if you're okay, will it always be the denominator? If you have x on top and it's being divided by 1.2, you want to like eliminate that 1.2. You want to you want to get x all by itself so that you know what x equals. So when we isolate, we call it isolating x. Whatever's on the bottom here, whatever's being divided by, we multiply by that same amount. So whatever's on the bottom, that's the number we multiply both sides by. So if that's your question, then yes, you're absolutely right. Awesome. Yes?
Would it be possible to put Joan's shadow and Joan's height on the top?
All right. Very good question. I am going to, that's the second sort of method of doing this that I was going to share with you. So I am going to do that now. And the question, if you didn't hear that at the back, was, is it possible to put all of Joan's information as a ratio on one side and all of the monument's information as a ratio on the other? And the answer is absolutely correctly yes. And to tell you the truth, when I look at a question like this, that's sort of the method that I gravitate to. So I'm going to do that as well. You can write this down if you want. You do not have to, but I will show you just down here the other sort of method. So if you have, so what I do is I look and I see the triangles. There's one, right? And the other one is the big one. Okay, fine. So what I do is I look at the ratio of the sides within one triangle, and I usually use that as a proportion. So if I go the vertical side of this triangle and the horizontal sort of bottom side of this triangle, I can use that as a ratio, and then I can compare that or equal that to the ratio of the sides of the other triangle. So you can do it that way as well. And so that would be written like this. It would be, let's say, Joan's, and I used her height, so Joan's height divided by Joan's shadow length. So yes, you could put all of Joan's information on one side of the equal sign and all of the monuments, so the monument height. The only thing you have to be careful with is the consistency of heights on top. You have to have the heights on top or both heights on the bottom. It doesn't really matter, but if the height is on top over here, the height has to be on top over here. And then you would put monument shadow here. So yes, you could. This is the other way that you could totally do it. And honestly, they're both exactly the same. The way math works, this is exactly the same as well. So if we do that, and again, I'll just make some space maybe over here and try and show you how to do that. So Joan's height, that would be 1.2 divided by 4.1 should equal monument height, x, over 20.5. Okay? And when we solve that, I think this is where you'll start to see why this is exactly the same, because when you start to solve this proportion and you multiply both sides by 20.5, these 20, whoops, what did I do? These 20.5s are gone. They divide out to 1. And look at what x equals in this method. X equals 20.5 times 1.2 divided by 4.1. And that's exactly the same thing that we had in the first method. You see that? It's just that the multiplication, the things you're multiplying are switched around, and that's totally fine. You can do that. So yeah, whatever stands out to you. You could do height over height, shadow over shadow. That's totally good. You could do Jones height over Jones shadow, monument height over monument shadow. You just can't mix things up willy-nilly and just go 1.2 over 20.5 equals 4.1 over x. I don't really know if there's any consistency there. I'll just do that. Okay, so you have to have some kind of plan, but yes, that's the other way that you could look at things. And for some, that, you know, sticks out a little bit more clear than the first way. So very, very similar. I hope I haven't confused anyone, but this method of putting all of Jones' information on one side and all of the monuments information on the other totally works as well. Okay, any questions about that? Oh, and if we do this, obviously x is going to be equal to 6 as well. And because we have units in the question, please make sure that you add units to your final answer when you're all done. Okay, so does that answer your question? That's what you meant, right? Awesome. Anybody else have any questions about that? No? All right. All right, you guys doing great. Okay, so one more example that we'll do here before I'll give you some more homework to work on and practice yourself. So this is a little tough on the diagram to see all the numbers, so I've got it out here for you to see. Okay, this is the same that's on the diagram that just didn't photocopy very well. So here's an example. Remember that the situation I described yesterday where you have a river and you have like points on either side of the river, and if you know certain information, you can calculate distances across spans that are impossible to like just take a tape measure and to walk across, right? You can't just like walk across the river with a tape measure and then measure the opposite side of the river. Like, so you can use math to help you figure some of this stuff out if you know some important information. So to measure the width of a river, a surveyor made the following measurements. What is the width of the river? What is the width of the river? So what we have in this situation is, this diagram here. And what I want you to notice is a couple things. That we do have similar triangles here. How do we have similar triangles? Well, in this type of situation, okay, where you have two lines that intersect like this, two straight lines that intersect, in that situation, and this is super important if you've never seen this before, this will come up again and again in math, where you have two lines that intersect, the angles that are opposite of one another are always equal. Okay? And that includes, it doesn't really matter in this question, but that includes these opposite angles as well. So whenever you have two straight lines, okay, if those lines are perfectly straight, what you can guarantee is that this angle will always be the same as this angle. And this angle will always be the same as this one. Okay? Vertically opposite angles are equal, or just opposite angles are equal when you have two straight lines that intersect. All right? That is super important, and that's going to help us to notice that this angle that I've outlined in, well, that was blue until I covered it up with red. So this angle in blue and this angle in blue, those are equal angles. Okay? Now, it does look like this angle right here is close to 90 degrees, and this angle is close to 90 degrees. Those are also corresponding angles. And so finally, this angle and this angle will also be equal. So we have some similar triangles, and here's how we can split those up. Okay, so let's find out what x is. Okay, we're trying to find out the distance across the river at this point. That's what the question's really asking. So I know some other information, and I'm just trying to find this span right here. So notice that these are all those are all measurements that are on the one side of the river. So someone actually could walk across here and measure this, and then measure this, and then measure this as well. But you just can't walk across the river and measure that. So now math can help us. All right, so let's set up a proportion or a ratio. And again, a couple different ways you could do it, right? Let's do the first way where we have corresponding parts to corresponding to similar triangles. So this side is going to go with this side, isn't it? Those two are similar. So let's set up a ratio, and I usually do the big one first. Doesn't really matter, but I'm going to do the big one first. So this 30.2 side and this 5.8 side go together. Does that look good to you guys?
Yep.
All right. So that ratio right there of corresponding sides here should equal a ratio of two more corresponding sides. So what are the two corresponding sides that are left, and which order should I put? Like, which one should I put on top? Which one should I put on the bottom? Who wants to help us all out here? Hand up over there first. Yeah.
You do the variable x on the top,
X on the top.
and corresponding angle is the JK, so it'd be 14. It'd be divided by 14.
Excellent, excellent. Thank you very much. So the X side is corresponding with this side. And so we put X, because we have the 30.2 on top, I have to put the X on top as well, and then divided by 14.6. Yes, that ratio is going to be absolutely amazing. So great job. Okay, so let's figure that out. So let's, now how do I get the X by itself here? What do I have to do? Anybody? Spread this around. How do I get X all by itself? Multiply. Yes, by 0? 14.6. Yes, I multiply both sides by 14.6. Excellent. Look at that. Whoops, not 1.46. Thank you very much. 14.6. Yeah, remember, this is just like the other questions that we were doing. So 14.6 over 14.6 gives us 1 over 1. So that's like it's gone out of the way. And now X by itself equals this. That's the same as cross multiplying, remember? So on our calculators, you can get your calculator out for this. Would be a good idea. 14.6 times 30.2 divided by 5.8. Okay. And I get 76.02. So if we're rounding, I think this question says round to the nearest tenth. So remember, everyone, the place values, these are the ones. This is the tenths right here. So we want to stop here. That's the last number we want to put. But we do have to check the one to the right to see if we round up or round down. Remember this? Because it's surprising how many high school students do not remember how to round properly. So let me just show you. 76.02. So that's our answer from the calculator, 76.020, and there's more. If I want to round this to the nearest tenth, that means that this is the tenth, and I want to kind of stop here, but I need to know whether to round that 0 to keep it a 0 or to move it up to 1. So I look at the next number, and how does this tell me what to do? Who remembers how we round there? Yeah?
If it's more than 5, you like round up.
Yeah.
But if it's less than 5.
Right. So if it's more than 5, you round up. If it's less than 5, you keep it the same. If it's exactly 5, generally what do? We go up. Yeah. So if it's 5 or over, we round up. This is 2. So my final answer is 76.0. I leave that 0 as it is because the 2 is not big enough to make me round it up. And I look at my units, and of course I actually did this before the question started, and I saw that they were all meters, so that was great. And so my answer must be in meters as well. The width of the river is 76.0 meters. Okay. Good idea to write a concluding sentence so that you make sure you're very clear. So let's practice that. So you would just say the width of the river, like I just said, the river is 76.0 meters. A word problem deserves a word sentence for a final answer, okay? And maybe when you're in grade 11, 12, I'll let you bypass that, but we'll see. Okay, so for now, let's do Word problems, good habit to work on. Okay, any questions about those two final examples in this lesson here? Any thoughts or questions? Any difficulties? All right, let me give you the rest of your assignment. I know you've all been waiting for that. So I'm going to ask you to do 9 to 12, and 15 is going to be optional. It's a little bit of an extension one, so if you get done 9 to 12 in this class, I would like you to try 15. I think everyone should try 15, but again, I will make that optional for you. All right, so that rounds off 7.4 lesson. Any final questions before you get started in your assignment? Mm-hmm.